a project that involves developing classifiers for the Zwicky transient facility variable sources. Just a quick overview of our presentation outline. First, go over some background, our project goals, and then I'll pass it on to Sungmin and Dragon to go over some of the classification algorithms, results, conclusions, and then have some time for questions and answers. So now I'll quickly go over some background. So really all the data that we've been working with has come from the Zwicky transient facility. And this facility has a 48-inch telescope located in Southern California. It first came to light in 2018 and observes the entire northern sky. Quick tidbit of info is that there are bi-monthly public data releases, with the next one coming in June of this year. This is just a cool chart that has really a taxonomy of all the different variable objects that have been found with ZTF. And one important thing to note is that there's been 45 ultra compact white dwarf binaries that have been found. And a couple of slides later, might explain why our group found that to be interesting. So now I'll quickly go over some of the data that is used to be able to extract some of these insights. So there are two main types of data. One of the types is photometry, which is shown, an example is shown on the left image there. This is also commonly known as light curves. And the second type of data is high resolution spectroscopy, which is shown in the right image. So some pre-processing is done on these types of data that I mentioned in the previous slide. And really what's going on is we're extracting features, so statistical properties. And then what's happening and what's really important are period finding algorithms that are ran on this data in order to engineer, extract some features that can be used to classify or analyze the data. The three period finding algorithms that this system uses is analysis of variance, Lumsgargle, and conditional entropy. Now I'll quickly go over some of our project goals. Three main goals to touch on here. One is quickly and efficiently classifying large-scale variable star data, training a new XGBoost binary classifier, as well as helping produce a classification catalog from the ZTF facility. Some quick things to note, and I touch on this in the taxonomy slide, is that the white dwarf and ultra compact binaries are interesting because white dwarf binaries that have periods of less than 1 hour emit gravitational radiation that can be detectable by LISA. And as I mentioned, 45 white dwarf binaries have been found through ZTF so far. And touching a bit more on white dwarf binaries, this is the graph that we see here shows basically if you have a white dwarf binary system based on the mass of the two stars, what can these two coalesce to? What happens once they merge? And we've identified three, I guess, important examples here. And the main one I want to mention is the one all the way on the top right. And the reason this one's promising and important is because it's a system of two very large white dwarfs. And basically, there's a chance, Dragon can touch on if it's a big chance or not, of them coalescing into a type 1a supernova. And this
Seems
is
likely and very exciting.
Exciting for the field. Cool. So I'll pass it on to Sungmin to touch on some of the classification algorithms.
All right. So for the classification algorithm, what we have is a individual binary classification model for each of the categories. This plot is a hierarchy of all the classification categories there are. At the higher level, there are two different levels, phenomenological and ontological. Phenomenological means that it only uses the light curve features to produce these categories. Ontological means that on top of the light curve observations, you use all the external information astrophysical properties of the source type to produce this category. And what we're doing is we're producing an individual binary classifier for each of these 40+ categories. So for variable, for instance, we're having one model that predicts yes or no for variable and for all other categories as well. And for these classifiers, we have two different classifier algorithms, deep neural network and also XGBoost. I guess we're all a little bit familiar with deep neural networks at this point, but a brief introduction, a very simple example would be a feed-forward neural network where you have linear layers, which are the arrows here, and nonlinear activations, which will happen at these circles. And if you have many hidden layers in the middle, then it'll become a deep neural network. And instead of having linear layers, you can have different types of layers. For instance, convolution neural networks will have convolution layers, max pooling layers, and and it doesn't even have to be a feed-forward architecture. You could have recurrent neural network where you would feed your output back into one of the layers. And deep learning can be used in supervised problem, unsupervised, or even semi-supervised problems. So it can be used for classifiers, it can be used for reinforcement learning, it can be also used for generative models, and so forth. And this semester, I came upon this very interesting paper that tries to explain why deep neural networks work so well. The paper is Deep Learning, a Statistical Viewpoint by Bartlett et al., published 2 years ago. And they try to explain deep learning from the viewpoint of minimum norm interpolation. What it means is that among all possible models that gives you a perfect fit, you're trying to go for a model that has the smallest norm. In some sense, it depends the norm, whether it be Euclidean norm or L1 norm, it depends on the setting that you have. But if you go for a perfect fit in an over-parameterized model, if you go for the minimum norm interpolation, then in many cases, what they have proven so far is for linear regressions, kernel regressions, and specific types of two-layer neural network that it will not overfit. Although it will overfit, it will still have good predictive performance. And so why is it the case for us is that many types of problems, what we do is we have an over-parameterized problem, and we use a gradient descent algorithm on it. And we start the algorithm with a zero vector. And for many problems, it has been shown then that solution with that specific setup will converge to a minimum norm interpolation. So, and for DNN as well, we have a very large model, complex model. We use a variant of gradient descent, usually stochastic gradient descent. And the default weights in PyTorch and TensorFlow, they're all very concentrated near zero. They're very close to zero. So also for our problem, it quite fits the description that we have for minimum norm interpolation. So I thought this was an interesting result in the theory part that I would want to share. And the second algorithm that we use is XGBoost, which is extreme gradient boosting. What it is basically is it's an ensemble method. So you have many weak models and you combine the results to produce a stronger result. So a model with a better predictive performance. And boosting takes ensemble one step further by not having just individual weak models. In each iteration of training a weak model, we use the result from the previous model to provide adaptive weights to the training samples. What we're doing is that we're putting more weights to the samples that we misclassified in the previous model, so that the next weak model will pay more attention to those samples. And XGBoost is a variant of boosting with a few extra tricks up its sleeves, which makes it so much better than traditional ones. But basically, the idea is the same. And the reason why we have two algorithms is that a very tailored and trained and a very highly tailored deep neural network will probably outperform all other algorithms. But in a very general setting, XGBoost has a pretty decent performance. So it's good to have both methods ready for our application.
Like Taylor, you mean like a specific type of signal?
Yeah. So for a specific type of signal, the architecture curated specifically for this problem, and a lot of hyperparameter tuning. But without that, at the initial stage, XGBoost usually will perform better, and it's easier to implement in most cases. So it's better. That's why.
And also in that case, even if it does outperform, some people may actually choose XGBoost just due to the higher explainability of the model.
Yeah. And also, the benefit of having two different models in our application is that first we can directly compare the results of these two models. If they agree, we're more confident that we're going in the right direction, because what we don't actually have an answer sheet to tell us whether our predictions are correct or not. And if they give us different outcomes, it means that these samples could be more problematic, some samples that we should pay more attention to. So that's one benefit. And another benefit of adding XGBoost to deep neural network is that although deep neural network will probably have good prediction, there's no really straightforward way to interpret what the model is providing. However, with XGBoost, we can extract feature importance, which indicates that which feature were most useful in the construction of the model. So we can provide some more insights into which features are more important for this classification category and something like that. And moving on to results. So what we primarily looked at is prediction outcomes in a binary classifier. So there's 4 different outcomes: true negative, false positive, false negative, and true positive. And our model gives us a score between 1 and 0. And we will predict, in this case, this is a result for pulsar category. We will predict it as a pulsar if the score is above a certain threshold. And we can change the threshold so that, so with a higher threshold and with the score 0.55, threshold at 0.5, we would predict it as a pulsar. That will be a true positive here. Threshold 0.6, we'll predict it as a negative. So it will be a false negative because in the case that its true label is actually a pulsar. So with different threshold, what we're doing is we're moving the vertical bar left and right. What we would ideally want is maximize the diagonal numbers and minimize the off diagonals. But you can see that if you move the vertical bars, one of them will shrink, but one of them will become larger. So it's not really easy to control both of them at the same time. Yes, sure. Oh, yeah. Oh, yeah. Maybe it was related to this slide. So you can use many different metrics to measure the performance of your classifier. The one that we specifically look at is the area under the curve of the receiver operating characteristic curve. That's a mouthful, but there's a lot of components involved with it. First, you would need the precision, which is defined as true positive over false positive and true positive combined. So that's true positive rate. No, recall is a true positive rate. And here we have the recall, which is true positive over all of the that are actually positive, true positive plus false negative. And for each of the thresholds, you plot the combination of precision and recall that you have, the ROC curve, receiver operating characteristic curve. And we just calculate the area under the curve as a measure of our performance. So what it does is that we're trying to look at a balance between the precision and recall. We don't want to focus on either of them too much. And as a balance, we're looking at the area under the curve. Usually you would have a decreasing function like this one. This would be one of the ideal case. It's quite unusual that you will see some increasing portions in the receiver operating characteristic curve. And but that's actually possible, although unusual. Recall will always decrease if you increase the threshold, but precision doesn't have to. Although this is the only time I've ever seen a receiver operating ROC curve that goes up, but that's still possible. And oh yeah, go ahead.
So in the case that you're looking at now, either whatever category you're looking at in classification, are you more interested in what we would call purity or precision, or are you more interested in a complete sample?
I'm not sure what you mean by complete sample.
So another way to cast precision is the purity of the sample.
Okay.
And recall is
Oh, okay.
so if you,
Completeness more in this case because it's one of many different binary classifiers, all of which we'll sort of look at together to determine the overall most likely object type, which we'll get into. But
okay.
Yeah, and also, since there are like 40 plus categories that we want to test out, and there are in some cases they're highly imbalanced, in some cases not. So, and at this point, we just wanted to use a uniform metric for all of these classifiers. So we just chose AUC, but depending on the specific category, whether it's more important to have more true positive or a false positive or false negatives, then in that case, we could have some more tailored metric specific for that type. And I'll take that on
And
to Charlie.
as Sungmin discussed, the RSC curve is a good metric of how good each classifier is at that particular source type. And the AUC curve, the AUC is the area under the RSC curve. And on the right here, that's actually for the DNN classifier over many series of training rounds. But if you like, for one test set, you can find the AUC as a single float, single number. And so we did run that on a test data set for both classifiers across all 44 possible object types. And they perform quite well, both of them. There are a few notable exceptions where we did not have very many true positives for these examples, and DNN requires quite a large input training data set. So we think that's probably why there's the large disparity there. And overall, on the rightmost column, the average AUC, it seems that XGBoost performs at least as well as DNN, and that is due in part to the smaller test data set, so we should increase our sample size as well. But one of the key benefits of XGBoost is that it's easier to test feature importance. So the F1 is the even-weighted harmonic mean of precision and recall for each particular binary classifier. If you have a higher F score, it's more accurate, but it's not necessarily best if the data is skewed, that is unbalanced. High recall in that case, you might want to look at precision instead. But we compare feature importance for all 44 individual classifiers on inference data, which is to say, in this case, DR5 from ZTF, which we have ground truth. We know what these objects are. So on the left, we have Cepheids, and on the right, we have eclipsing main sequence binaries. The most important statistical feature for Cepheids appears to be period, and for eclipsing main sequence binaries, the number of ZTF alerts, which is when a new image differs from the reference historical image by more than 5 sigma. An alert is generated for all sources within 2 arcseconds of that. And a variety of other statistical features are important as well. We really need to compare across all objects in the data set and all object types. There are limits to this, which is if you do traditional rank-based classification method, you take for a given source ID that you have 44 different object types it could be with an array of probabilities. If you were to just take the top probability there and say, oh, it's this type of object, you'd be incorrect in the case of XGBoost, because XGBoost has independent binary classifiers as each of the 44 nodes. They have no knowledge of each other, so you can't go backwards. It is also one of its strengths, though, because you can therefore determine each individual classifier has tuned hyperparameters for that object class, and that means that it's judging all statistical features equally for each case, and you can compare classifier performance without worrying about the fact that it can't compare between forks. And by that metric, we can just add possible labels with a given threshold, maybe everything above probability of 0.7, we can add, oh, it might be this, and then look at all those labels for each source ID to determine the most likely object type. So we've discussed why identifying these ultra-compact binaries are useful. Initially, the end goal is to compare 2 independent measurements, gravitational and electromagnetic, of course, but in the meantime, there are a lot of things we can do. We can estimate population rates of white dwarf binaries and hopefully prove the type 1a progenitor hypothesis, that is that these 2 white dwarfs might merge into type 1a supernovae if they're very large white dwarfs. We can also, of course, contribute to our field guide of variable stars in the Milky Way. So to do that, we finalized our training set through additional active learning rounds, which means after a training round, we sent these objects to people, experts in the field, to identify whether or not the labels were correct. at which point their input was put back into another training round, as well as making that upload download process easier so they don't have to spend too much time on it. And now we can run this XGBoost in parallel to DNN to classify new objects for which we don't know ground truth. According to test AUC, XGBoost performs at least as well as DNN, so it's looking quite promising to be able to compare whether or not they agree and verify if we need to go train one or both of them again. So the immediate next step is compare those statistical features across a larger data set, firstly, and across each object type for a large average of many different objects. And we will be running it, as I mentioned, on the latest data release in June. And another thing that we should do software-wise is probably cross-match CTF IDs. So something that sometimes happens is that CTF takes images in G, R, and I band. So that's already 3 images of the same source. And also sometimes you have overlapping fields to deal with chip gaps. So more than one ZTF ID is associated with each actual object. So we need to have an automated system that goes through and verifies that it's actually the same thing. Thank you. Question?
Next slide.